Hi everyone, welcome to this presentation about energy efficient architecture for receive spatial modulation in large MIMO systems. I am Ahmed Raafat, PhD student at UBC Barcelona and researcher at the 5G wireless project. The results in this presentation is made available by the great support from the 5G wireless project. Let's start with brief motivation. 5G wireless technology will enable machine-to-machine communications along with additional Internet of Things applications, so it's expected that billions of devices will communicate wirelessly in the future, and this requires high data rate links to communicate at low latency. Millimeter wave frequency band is one of the most promising key technologies for future 5G system, as the availability of unused large bandwidths can allow high data rate links. However, many challenges have to face to efficiently adopt this technology for wireless cellular systems. The main issues with millimeter wave propagations are first is a severe bus loss. Millimeter wave propagations suffers from a severe bus loss. As we can see in this table, there is around 40 dB more bus loss in the millimeter wave frequency band. But the small wavelengths of millimeter wave signals permit backing large number of antennas not only at the base station but also at the user terminal, which provides high beamforming gain to combat this bus loss. For example, at 3.5 gigahertz, we can put four antennas. In the same area, at 28 gigahertz, we can back 256 antennas, which improves the beamforming gain to combat the bus loss associated with millimeter wave propagation. The second constraint at millimeter wave is the massive MIMO transceiver design. Uh, in this figure, this is the conventional massive MIMO transceiver design based on fully digital architecture where each antenna at the base station and at the user terminal is connected to RF chain and analog to digital converter. And as we can see in the table below, that RF chain and ADC are the most power consuming devices, especially at millimeter wave frequency. So this architecture is power consuming and also expensive at millimeter wave band. So conventional MIMO becomes challenging at millimeter wave frequency band. Hybrid MIMO have been proposed with the aim of simplification of the massive MIMO transceiver design in millimeter wave band. The idea of the hybrid MIMO that part of the processing occurs in the baseband using digital processing, and the other part of the processing occurs on the passband using analog processing. So the processing is divided between the baseband and the passband, between the digital and the analog. And the analog processing occurs by using of phase shifters. So the idea here, they reducing number of RF chains and they put large number of phase shifters because the power consumption and the cost of the phase shifter is much lower than the RF chain. The advantages of this architecture is the high spectral efficiency approach the conventional MIMO, but the drawback that the power consumption may increase rapidly with increasing number of RF chain, maybe higher than the conventional MIMO architecture. What we are proposed now is efficient massive MIMO transceiver architecture in millimeter wave frequency band. We will discuss a low complexity receive spatial modulation massive MIMO, novel detection methods aimed to increase the throughput, TDD frame design followed by simulation results. This is the proposed low complexity receive spatial modulation massive MIMO. We are proposing here to simplify the user terminal circuit, we use only one RF chain and one high resolution ADC at the user terminal. As we can see here, this is the high resolution ADC and this is the RF chain. Only one RF chain and one high resolution ADC. And this amplitude detector works in the millimeter wave band, measures the amplitude of the RF signal with negligible power consumption. And this 1-bit ADC consumes very low power. And the circuit in black is a downlink circuit, and the circuit in link is the uplink circuit. And this scheme based on the fully digital base station. The aim of this scheme is to simplify the user terminal circuit and at the same time exploit the spatial dimension at the user terminal to transmit extra spatial symbol in order to achieve a high bit rate. So in this scheme, millimeter wave channels are highly correlated. So we consider receive antenna selection at the beginning. So we activate NA antennas out of NR at the user terminal in order to combat the correlation between the receive antennas. And the amplitude detector and the 1-bit ADC are used for the spatial symbol detection. The RF chain and the high resolution ADC are used for the modulation symbol detection. This is a quick example about the transmitting and detecting the spatial symbol. We transmit here X is a modulation symbol, SI is a vector, contains ones or zero. It's like exactly the spatial symbol we transmit. B is a zero forcing precoder, H is a channel matrix, B the average transmit power, and alpha is a normalization factor. So YK is the received signal per case antenna. The case antenna can receive the modulation symbol X if the spatial bit is 1. Otherwise, the receive antenna will receive only noise. So let us consider this example. The input data bits is in black, divided to the red bits, which referring to the spatial symbol, and the blue bits, which referring to the modulation symbol, maybe from QPSK constellation or any QAM constellation. So now, if the first spatial bit is 1, the first antenna will receive the modulation symbol X. The second spatial bit is 0. The second receive antenna will receive 0 signal on, and third spatial bit is 1. Third antenna will receive the modulation symbol X. Fourth spatial bit is 0. Fourth antenna will receive 0. So this is the mapping. Now, how to detect the spatial symbol? The amplitude detector can measure the amplitude of the RF signal at millimeter wave frequency band. After that, we compare this amplitude with a predefined threshold through the 1-bit ADC. If the amplitude is greater than the threshold, so the detected bit is 1, otherwise the detected bit is 0. And by this way, we can recover the spatial symbol. For the modulation symbol detection, we first detect the spatial symbol, and after that we detect the modulation symbol. So if the spatial bit is 1, this switch will be closed and the modulation symbol will be allowed to go to the RF chain and the ADC. Otherwise, if the spatial bit is 0, the noise will be rejected. After that, all the signals here will be summed and go to the RF chain and the ADC in order to detect the modulation symbol. By this way, we can cover the spatial and the modulation symbols. In the TDD frame design, we propose at initial uplink training. The objective of this uplink training that the user terminal, this is the user terminal circuit, transmit biload symbols to allow the base station estimate the channel state information. And after that, because the millimeter wave channels are highly correlated, so the base station decides which antenna at the receiver side are active. After that, the base station inform the user terminal about the active antennas, the active receive antennas. Okay, so the base station inform the user terminal about the active antennas. So this is the best antennas that they will be active, and the other bad antennas will be silent during the transmission. And also during the downlink training, the user terminal estimate the threshold, the 1-bit ADC threshold. After that, we go through the downlink data transmission. Now I will talk about the simulation results. This figure show the power consumption versus number of receive antennas for the proposed in blue, the hybrid in red, and the conventional MIMO in green. So as we can see, when the number of receive antennas increase, the hybrid architecture may consume power more than the conventional MIMO. It depends on number of RF chains, and our proposed scheme is the most power efficient. And this graph shows the bit rate of the proposed and conventional and the hybrid MIMO. So the conventional is the best. The hybrid MIMO approaches the conventional. Our proposed architecture achieves moderate bit rate, but it consumes a very small power consumption. So this graph shows the energy efficiency. The energy efficiency is defined as the bit rate divided by the receiver power consumption. We are considering number of transmit antenna equal 32, bandwidth 1 GHz, transmit power equal to 40 dBm, pass loss 120 dB, and the bit error rate 10 power negative 5. As we can see that the proposed architecture is the most energy efficient, while the hybrid is the worst. That's all for the technical presentation. For the future work, we are thinking to develop a low complexity receive antenna selection algorithms, and we also thinking to reduce the hardware complexity at the base station, because in this work we are considering fully digital base station. This is an interesting publications related to our work in the area of the receive spatial modulation, generalized spatial modulation, and pre-coding for millimeter wave signals. This is interesting articles. Thank you very much for your attention. For more information about the 5G wireless project, follow us in YouTube and visit our 5G wireless website and our group in Twitter. Thank you.